Hey everybody, welcome to Existence and Uniqueness Proofs with me. Big idea today is we want to prove statements that have phrases like there exists or there is exactly one, which is the same thing as there exists something that's unique. We've done a lot of universal actually. We haven't formally addressed it, but we will also address this one a little bit, but not for very long. So let's get started. Let's first talk about existence. How do we prove that there exists an X such that this statement P of X is true? Remember back from our rules of inference day, we briefly talked about, It's existential generalization. That's the statement right here. Don't need to know its fancy name. You need to understand why it works. Basically, if you can find or construct a candidate that does satisfy this, then you have proved that such an X exists. The other way to go about proving existence is to prove that if it doesn't exist, then something absolutely absurd happens. So that's proof by contradiction. First example, we are going to prove there exists a solution to x squared minus 7 equals 0. This is a very easy direct proof. Here, we should probably label him. We're doing him directly. So my candidate, the one that I'm going to suggest, is x equals the square root of 7. We check that it satisfies P of x, which is x squared minus 7 equals 0. He does indeed. So last thing to check is it a real number? Yes. Square root of 7, you may take that for granted, that is a real number. So since we've got it's a real number and it satisfies our P of x, we have found our x that works. It's not the only one. We could have done negative square root of 7. That is also a perfectly good candidate. So we can say such an x exists. And we're done with our proof. It's that easy. Let's try another proof. There exists an integer between 0 and 9. We'll say that integer is n. That appears in the decimal expansion of pi an infinite number of times. So we know that pi is 3.14159.265. I don't know. Goes on forever. And it kind of makes sense, if you think about it for a second, that there's going to be a number in here that has to be repeated an infinite number of times. I'm pretty sure that they're all repeated an infinite number of times. But you have to have at least one, otherwise it would be finite. And that's basically going to be our argument. We're going to be without going through and saying here's infinitely many 2's in our decimal expansion of pi, we can't prove it directly. So this one will be indirect. I promise I can spell. It's a lie, I cannot spell. Okay. So for indirect, we're going to do proof by contradiction. Proof. I'm going to say by contradiction. So that means we get to assume that all of the numbers are going to show up finitely many times. So for any integer n, where n is between 0 and 9. Not for any, sorry. Any integer n between 0 and 9 appears finitely many times. And now if you look at this, this is actually a universal statement. Any is a for all. So for all n that's in here, and an integer. We're claiming that it's only going to appear finitely many times, which means we can count them. So then I'm going to make a little chart. So if we are looking at the integer n equals 0, I could say number of times it appears. I don't know how many, I just know it shows up a finite number of times, so I'll say it's k0 number of times. And then we'll say the number 1 shows up k1 times. Number 2 shows up k sub 2 times, and then that just goes all the way up to 9. And we'll say that shows up k sub 9 times. Where all of our k's are going to be integers, positive integers. Okay. Or, yeah. Okay. So that means at this point, we can go ahead and get the whole, oh, let's add up the number of digits and get that pi is finite thing. So then number of digits in pi is equal to k0 plus k1 plus k2 up to 9. And then we're going to say, how do you want to say this? Like this, if it was going on forever, we wouldn't be able to guarantee that it doesn't eventually add up to infinity. So like you take 1 and you add 1 to itself infinitely many times, you're going to get to infinity eventually. But this stops. It has a very clear stopping point. We're going to take 10 numbers and we're going to add them up. We know that's going to be finite. So we can say the sum of finitely many integers is finite. Okay, so that's very fancy words to go with this. If you had just done it's less than infinity, I totally would have accepted that as justification. So then pi is finite. Now we get to say contradiction. No, that's not true. Which means we must have been wrong at least one integer between 0 and 9 appears infinitely many times. And we are done. Cool, cool, cool. Okay, so that's really all there is for existence. You do it directly, you find a candidate, or you do it indirectly and prove it's absurd. On to universal. So we've actually been doing this, but let's very formally acknowledge it right now. We have what we've been using for the most part is like if P of C is true for any arbitrary C, we get that it's always true. So as long as we don't put any special restrictions on our number that we're trying to use, then it must work for all of them. So this was universal generalization. Again, a rules of inference law that we're using. It's why this argument gets to work, because it's logically valid, and you do not have to cite it. We can also do it indirectly. We've done this a little bit too. We've done contradiction. We've done contrapositive. Let's go ahead. We'll do one example. And since we've done a little bit of universal stuff before, I'm going to do something that's a little bit new. I'm going to say for any integer, n is even if and only if n squared is even. So that's new because we haven't done an if and only if in the lectures before. Hopefully you've read about it. But just in case it's a little bit unclear, here we are. So whenever you have to prove an if and only if statement, remember you guys proved that P if and only if Q was the same thing as doing P implies Q and Q implies P. And so all you have to do is prove that statement, prove that statement. If they're both true, then you get the if and only if. So if and only ifs pretty much always come in 2 steps, proving it one direction, proving it the other. And there's usually an easier direction. Try reading it both ways and decide which direction is easier and go for that one first. So here we go. For all n is even if and only if n squared is even. Let's think about the forward direction. N is even if and only if, or if n is even, then n squared is even. And to prove or set this guy apart, this is the direction that I'm proving. So that would be the forward direction. N being even implies n squared is even. And then that's a really easy plug and chug. Suppose n is even, then n equals 2k, where k is an integer. And then n squared equals 4k squared, which is just 2 times 2k squared. That is an integer. So then n squared is even. And we're done with that direction. So that was an example of a direct proof. And then this direction would be n squared is even. If n squared is even, then n is even. This one will be indirect. Sorry. Okay. Moving on. This one is going to be an indirect proof. It's really hard to go at it head on. So we could assume, I will write down the assumptions. We could do contrapositive. That would mean we could do n is odd, then n squared is odd. And we could prove that instead. That would be really quick. Keep forgetting to write my ifs today. There we go. And then you could also do, we'll say, contradiction. And that would be assume that n squared is even and n is odd. Either way, you get to assume something about n itself instead of just n squared, which is going to give us that ability to, write n using 2k or 2k plus 1, plug it in, see what happens. Okay, so this one would be indirect. I'm not going to prove it because you guys already proved it on your worksheet. I'm going to say QED. We are done. Okay. Now we have uniqueness. That's when we get this cute little exclamation point involved. And the way we prove uniqueness, that comes in 2 steps. Step 1, prove it even exists. Because if it doesn't even exist, then it definitely doesn't exist uniquely. And then after we prove that it exists, we have to show that it is the only one that's going to work. Okay, let's see if we can take this for a run. Example 4, we want to prove that there exists a unique real number that solves this equation. So first thing we gotta do is we gotta find a candidate. So existence. If you don't see it off the top of your head, that's fine. We can go ahead and find a candidate because we know how to solve algebra. And hopefully we remember how to factor. All right, so we know that that is going to be x equals 1. We know it's going to work. We know it's going to be the only solution, but we have to still prove it. So suppose x equals 1, then 1 squared plus 1 equals 2 times 1. Check. 1 is a... there's no reason I can't start up there. 1 is a real number. 1 fulfills what we want. So then x equals 1 satisfies, let's say, our equation. So we are done with the existence part of this proof. Now we have to prove uniqueness. So the way we do uniqueness is basically we say, well, what happens if there are two? And then we work down until we have eventually proven that, if there's two, then they must have been the same one all along. Therefore, it is unique, because if there was a second one, it would still be that one. Okay, so for uniqueness, we're going to go and do... let's start the next slide. Let's do suppose A and B are in R and both satisfy x squared plus 1 equals 2x. So that means if we plug in A, we're good. And if we plug in B, we're also good. What can we do? Well, I see an and sign, so there's got to be some sort of way to put them together. So I'm going to say, well, let's subtract that over. Same thing for this one. And then now we have two things that are equal to 0, so we can set those guys equal to each other because they're both true because it's connected with an and. And those ones are going to cancel out. Let's see, we can rearrange a little bit. We can do a squared minus b squared minus 2a minus b. And then this, remember, is like a minus b times a plus b. And so there's an a minus b hidden in there, so I'll factor that out too, which leaves us with a plus b minus 2 is equal to 0. So that means we get down to a minus b equals 0, or a plus b minus 2 equals 0. So this one, that is obvious that a equals b. This one is just oh man, that doesn't give us a equals b, does it? It does. So how do we finish the proof at this point? We have to break it into cases. That's what an or means. It means they're not true at the same time. It means one of these things or the other thing is going to happen. And so case 1, a minus b is equal to 0. A equals b, just by moving the b. We're done. Case 2 is going to require some finesse. He's a little bit longer. but that's okay. We got this. Case 2. A plus b minus 2 is equal to 0. So what we can do at this point and say solve for one of our variables, say a, and then go ahead and plug it back in all the way up there. So then that would be 2 minus b squared plus 1 is equal to 2 minus b. And then now we've plugged it in. Now all we've got to do is a bunch of simplifying. Let's see, those 4's cancel. So then b squared minus 2b plus 1 equals 0. So then b squared is 1. But then now I can come back up here. I can say a equals 2 minus b, which is equal to 2. Oops. Sorry, I should not have written that squared down there. 2 minus 1, which is 1. So a equals 1, which is equal to b. So there you go. We have a equals b again, which means if we were to have two different things that satisfy our equation right here, in the end, we're going to find they have to be the same thing. So bam. Okay. So that's existence. That's universal stuff. That's uniqueness. What if we start putting things together? What happens? Multiple quantifiers. We can still deal with it. So example 5. Between any two rational numbers is another rational number. First step to this is just understanding what the problem is trying to say. I feel like it's easier to interpret with quantifiers. So we've got a rational number. We have another rational number. And then I'm claiming that there exists a w that's going to be in between those two rational numbers. And then I was able to just say that x is less than y because it's a rational number and it's a rational number. One of them has to be smaller since they're not going to be equal. I guess to make this a little bit more explicit, it should say between any two distinct. I had meant to put that in, and then I must have forgotten by the time I got back to this problem. Okay, so between any two distinct rational numbers, which means they're not equal, which means one of them would have to be bigger than the other. Doesn't matter which one it is. Okay, let's brainstorm. This is an existence proof. That means I need to find a candidate. You could go at it indirectly, probably, but directly is always better when possible. So let's try directly. I'm going to say that halfway in between x and y is a good place. So halfway in between. So what would be halfway in between? Their average. So I have a guess, I have a hypothesis, but I have to prove this works. I have two things to prove. A, the average is indeed going to be in between x and y. We know it, but we have to prove it. And number 2, I have to prove that this is still a rational number, because just because it's in between them doesn't make it good enough. I need another rational number to be in between. Okay. So I'm good. I've got my hypothesis. Let's roll. So first, let's go for proving it's in between. We start with x is less than y, because that's our premise. If x is less than y, we're going to get this. I'm not starting with this. I'm going to end with that. So if I add y to both sides, that's going to be x plus y is less than 2y. So then x plus y divided by 2 is less than y. And then I'm going to repeat this again. I'm going to do it by adding x to both sides. X less than y. I'm going to add x to both sides, so that's going to be 2x is less than x plus y. X is less than x plus y over 2. And I'm just going to connect these statements with ands. So we have that in the end. Okay, why did I connect them with ands? Because this statement is x is less than w and w is less than y. And then the reason I could do that here in the beginning is because the beginning statement is really x is less than y and x is still less than y. So we can just double say it. And then we can add things to both sides, and we can add different things, and that's totally okay. And we're able to get that it is indeed going to be in between our x and y. Okay, so it's in between. Now we just need that it's a rational number. Okay. Nope, I do not have more space. Let's make more space. So, since x comma y are rationals, let's take advantage of that fact and write them in their fraction form. And then we want to quickly note that b and q are not going to be 0 because those are the denominator. Okay, so then now we have x plus y over 2 is going to be equal to p over q plus a over b all over 2. And then that's going to be equal to pb plus aq over bq all over 2. And then we can simplify that just a little bit because we need a single fraction in order to do rational numbers. There we go. So then pb plus aq and 2bq are going to be integers. So we need integer over integer, so that's good. And then 2bq doesn't equal 0 because 2 isn't 0, b isn't 0, q isn't 0. So yes, taking the time to write that down was good. So we have our two qualifications. So then w equal to x plus y over 2 is a rational number such that x is less than w, which is the average, less than y. All right. So that was everything we needed to prove for this. Again, you could have gone at it with negation if you didn't see the direct way. That will also result in something, and then at that point you have to like try and prove that something ridiculous is going to happen, and sometimes it's easier to prove ridiculous things happen than finding a good candidate. Okay, that's all I've got for right now. I'll see you guys next time.